Welcome to the last lecture of Force and Laws of Motion. Uh, this is physics. Physics have never been easy. As of now, what I want you to do is understand the three parts, the three lectures online, and then go through the textual question answers and numericals on your own. Ask me doubts if you have. But once we open normal tuition classes, which is hopefully after Diwali, at that time I will redo the entire chapter. And when I redo the chapter, I will go through each and every numerical, each and every question answer from textbook. But as of now, focus more on understanding the concepts and then preparing question answer for the first term exam, which most probably will be after Diwali. Force and laws of motions का एक complete revision करते हैं. We know that force is a kind of push or it is a kind of pull. Any kind of push or pull is force, and force leads to changes. Force can lead to change in shape, change in speed, change in direction. It can make stationary things start to move, or it can make moving things stop. That's all what force can do. And there are two types of forces: balanced forces and unbalanced forces. Balanced forces are those opposite forces which are equal to one another but in opposite direction. So if I'm pulling the block with 10 Newton force in this direction and at the same time same 10 Newton force in opposite direction, will this move? No, it will not move, it will remain where it is. Because in balanced forces, the net force is considered as zero. Imagine two children pushing the box. They apply 10 Newton force. The box applies 10 Newton back to them. Therefore, the force is balanced. Therefore, box does not move. They increase their force to 30 Newtons. The box is capable of giving back 30 Newtons. Balanced forces. Therefore, the box does not move. But the children exceed their force to 50 Newtons and box can apply only 30 Newtons. Therefore, there is a net force of 20 Newtons. 50 minus 30, 20. The box will move. And this kind of force is called unbalanced forces, जहाँ पे एक force ज़्यादा एक force कम. Another question: why was the box able to provide force? Box कोई जिंदा चीज़ नहीं है. Box सामने कैसे प्रेशर दे सकता है? ऐसे that box and the ground has friction between its surfaces, and this friction is a kind of force which is present everywhere on the planet. Galileo conducted some experiments and concluded कि बॉल को अगर एक स्लोप पे एक पर्टिकुलर हाइट से फेंको तो वो बॉल तब तक ऊपर जाएगा जब तक वो सेम हाइट नहीं पहुंच जाता. दिस इज द फर्स्ट कंक्लूजन कि जो हाइट से फेंकोगे वो हाइट तक पहुंचेगा. इफ़ यू थ्रो अ ग्रीन बॉल फ्रॉम दिस हाइट, it will go down and go only up to this height. It cannot cross that limitation. फिर गैलीलियो ने स्लोप्स बदले और स्लोप बदल बदल के देखा तो भी वही कंक्लूजन दैट हाइट अचीव्ड बाय द बॉल इज सेम. देयरफॉर ही केम टू अ कंक्लूजन कि अगर वो स्लोप निकाल दे, अगर वो स्लोप रखे ही नहीं तो क्या होगा? द बॉल विल नेवर स्टॉप. इफ देर इज नो स्लोप, द बॉल विल नेवर अचीव द हाइट, and if ball will not achieve the height, the ball will never stop. Therefore, something which is moving continuously keeps to move. और न्यूटन ने उसको समझ के फर्स्ट लॉ दिया, which is also called law of inertia. The first law of Newton says that an object at rest remains at rest, object in motion remains in motion, unless an unbalanced force acts on it. कैरम बोर्ड में सारी डाइस सेंटर पे आराम से बैठी थी एंड दे वर नॉट मूविंग. दे डिड नॉट वांट टू मूव, बट एन अनबैलेंस्ड फोर्स वाज एक्टेड फ्रॉम द स्ट्राइकर. और जब स्ट्राइकर ने एक अनबैलेंस्ड फोर्स दिया तो नीचे की जो डाइस है उसका इनर्शिया हिल गया उसने जो डिसीजन लिया था दैट आई एम नॉट मूविंग एंड आई विल नॉट मूव, वो डिसीजन रॉन्ग हो गया एंड इट केम आउट। बट बाकी वहीं के वहीं रह गए बिकॉज बाकियों का इनर्शिया स्ट्रॉन्ग था, सॉलिड था, एंड उस पर कोई डायरेक्ट अनबैलेंस्ड फोर्स लगा नहीं था। देयर फॉर दे ऑल रिमेन वेयर दे आर, दे जस्ट फॉल डाउन लाइक दिस, दे डोंट मूव। दैट्स लॉ ऑफ इनर्शिया। हियर ऑल्सो द कॉइन वॉज फॉलोइंग द लॉ ऑफ इनर्शिया। कॉइन ने डिसाइड किया था कि मैं ग्लास के ऊपर हूँ और मैं यहीं रहूँगा। कार्ड ने भी डिसाइड किया था दैट आई एम हैप्पी द वे आई एम, आई वॉन्ट टू रिमेन हियर। बट an unbalanced force was acted by the hand, and when hand acted with unbalanced force, तो कार्ड का जो इनर्शिया है वो ख़त्म हो गया, इसलिए कार्ड गया फुर। और जब कार्ड फुर हो गया तो कॉइन साथ में फुर नहीं हुआ बिकॉज कॉइन और कार्ड के बीच में जो फ्रिक्शन है वो बहुत बहुत कम था। देयर वाज सच स्मॉल फ्रिक्शन दैट द कॉइन रिमेन्ड वेयर इट इज, बट coin cannot remain where it is without a base, therefore coin fell down. So this is the law of inertia or first law of motion. Then Newton gave then there was relationship between inertia and mass. Imagine, आगे एक वीडियो देखोगे तो ज़्यादा समझ में आएगा। एक बस है which is going at 5 meter per second speed, और एक मच्छर है which is also going at 5 meter per second speed. Both hit a wall. What do you think will happen? If bus hits the wall will break. But if mosquito hits the wall will not break. कहने का मतलब है मास से बहुत फर्क पड़ता है। Mass of the bus is higher, therefore it can create more force and it can create more momentum. मच्छर का मास कम है, therefore less force and less momentum. Similarly, imagine a small boat which can easily be handled by a human being versus a giant steamer which is not so easy to manage. Why? Because giant steamer has large mass and the boat has small mass. तो भले दोनों की वेलोसिटी सेम है, 5 मीटर पर सेकेंड, वेलोसिटी इज़ 5 मीटर पर सेकेंड, बट ज़्यादा मास डेंजरस होता है क्योंकि उसके पास ज़्यादा मोमेंटम है। सो सेकेंड लॉ ऑफ मोशन टेल्स अस अबाउट मोमेंटम, दैट मोमेंटम इज इक्वल टू मास इनटू वेलोसिटी, P is equal to mv. And second law of motion says the rate of change of momentum, matlab change in momentum with respect to time, is equal to the unbalanced force acting on it. Then there is a small derivation which you have to do. You know why the cricketer moves his hand when he catches the ball? Because if he catches and does not move his hand, the force created is very large. It might harm him. But when he moves the hand, he is giving more time. And when you give more time, the force created on the hand is less. Therefore, it will not damage his hands.
Momentum is inertia in motion. A lot of momentum means a lot of oomph. An even better way to describe momentum is as the product of mass times velocity. This means that if something is moving, there are two ways to affect its momentum. One, there's the mass. You know, for the same speed, a massive truck has so much more momentum than a mosquito. And two, look at the velocity. A baseball thrown gently by a kid will be easy to catch. That same baseball, thrown at 100 miles per hour, might knock you over. So a tiny bullet at a high speed has a lot of momentum. Wear a bullet vest and it'll still knock you over. An oil tanker creeping along at only a few miles per hour also has a lot of momentum, not by virtue of its speed, but by virtue of its great mass. because it has so much momentum, so much inertia in motion, the tanker can't just pull into the dock. Rather, it's greeted by powerful tugboats that help to manage its maneuvering. A fast-flying tiny bullet and a creeping massive oil tanker are both difficult to stop. Both have a lot of oomph, that is, a lot of inertia in motion, which you now know to be what we call momentum. Good energy.
Let's do third law of motion today and law of conservation of momentum, two topics, and finish the chapter. Third law of motion is a very simple statement. Action and reaction are equal and opposite. The simplest example of third law of motion is टेबल पे पड़ी हुई एक बुक. टेबल पे जब बुक पड़ी है तो हाउ इज थर्ड लॉ अप्लाइड, आई टेल यू. द बुक हैज सम मास. लेट्स से द बुक हैज मास ऑफ 1 kg. The book is under gravitational force and it is F1. So the book is applying force on the table. The table is applying equal force in opposite direction to the book. The book is called action. The table force is called reaction. And action and reaction are equal and opposite. Therefore, the book does not fall inside the table. At the same time, book does not fly off from the table. Book जहाँ है वहीं पे है because balanced forces are there. और याद करो, पहले भी किया है, balanced forces जहाँ पे होता है वहाँ motion नहीं होती. जो जैसा है वैसा रहता है according to first law of Newton. So the book is applying force on table, the table applies force on the book. One more example of third law of motion. There is a wall and this is me, जो जनरली मैं क्लास में लाइव करके दिखाता हूँ. I am pushing the wall. Me pushing the wall, will the wall break? No, because when I push the wall with say 100 Newton force, the wall pushes me back with same 100 Newton force in opposite direction. This balances the forces, और balanced force में कोई मोशन नहीं होती. बट इमेजिन करो मेरी जगह पे ड्वेन जॉनसन, हॉलीवुड का सल्लू भाई, ड्वेन जॉनसन हेल्प्स मी इन पुशिंग द वॉल. एंड व्हेन ही पुशेस द वॉल, he has tremendous force, 1000 newtons. And maybe the wall is not that strong. It can only give back 500 newtons more. Now this is a case of unbalanced force. इस तरफ से 1100 न्यूटन फोर्स is acting and the wall is able to give back only 600 newtons. Net force is 500 newtons in this direction और ये extra force है, therefore the wall will fall. Now imagine, instead of this, what will happen if there is a curtain, पर्दा, और पर्दे पे मैं मेरी पूरी बॉडी का वजन दे के फोर्स दे रहा हूँ. व्हाट डू यू थिंक विल हैपन? आई विल फॉल डाउन. क्या है पता नहीं, बट आई फेल डाउन. व्हाई विल आई फॉल डाउन? बिकॉज माई बॉडी इज अप्लाइंग फोर्स ऑफ से 100 न्यूटन्स, बट द कर्टन इज वेरी वीक. इट कैन ओनली प्रोवाइड बैक 10 न्यूटन फोर्स. तो एक्स्ट्रा 90 न्यूटन फोर्स की वजह से पर्दा जाएगा उड़ और मैं जाऊंगा गिर लाइन देखने. दैट्स कॉल्ड थर्ड लॉ ऑफ मोशन. एक्शन रिएक्शन आर इक्वल एंड ऑपोजिट. लेट्स टेक दिस फर्स्ट डिस्कशन अबाउट टू वेइंग स्केल्स. एक वेइंग स्केल को अब दीवार पे जड़ दो, दीवार पे फिक्स कर दो. सो दिस साइड इज द वॉल and this side it is you. हैव टू बैलेंसेस, टू स्प्रिंग बैलेंसेस जो मेजरमेंट दिखाते हैं कितना केजी फोर्स लगा एक्सेट्रा. नाउ start to pull in this direction, and when you start to pull, it shows a certain level. You will realize the same amount of level is shown on the other side also, because the wall is also pulling in opposite direction. If you pull with 100 newton force, the wall will also pull with 100 newton force in opposite direction. Both the forces are visible on this spring balance. अगर 1100 पुल किया तो वॉल स्ट्रांग है तो वो भी 1100 पुल करेगी. इट विल बी हायर बट इट विल ऑलवेज बी सेम. F1 इज इक्वल टू माइनस F2 कहते हैं इसको. F1 इज इक्वल टू माइनस F2 मतलब द फोर्सेज आर सेम बट एक नेगेटिव और एक पॉजिटिव, मतलब डायरेक्शन अलग अलग है. इमेजिन द सिनेरियो ऑफ यू जंपिंग आउट फ्रॉम अ बोट. एक बोट से जब तुम जंप मारते हो डेक पे तो बोट पीछे जाती है और तुम आगे. यू आर गोइंग इन फ्रंट बिकॉज यू अप्लाइड 100 न्यूटन फोर्स, बट द बोट गोज बैक बिकॉज सेम फोर्स इज अप्लाइड ऑन द बोट ऑल्सो बिकॉज ऑफ योर लेग. दिस इज एक्शन एंड बोट गोइंग बैक इज रिएक्शन. बट एक चीज इमेजिन करो, इफ यू आर जंपिंग फ्रॉम अ बोट, डेफिनेटली द बोट गोज बैक and you go front. But if you are jumping from a huge steamer, you will go in front, but do you think the boat will go back? No, the steamer does not go back. Why is the question. ऐसा सेम why मैं गन के केस में भी पूछ सकता हूं और फिर मैं एक्सप्लेन करूंगा कि क्यों ऐसा. There is a gun and the gun has the capacity to fire the bullet. बुलेट एक छोटा सा मेटल का टुकड़ा होता है and the gun can fire the bullet. The bullet goes in this direction और gun comes back, which is called recoil force. गन थोड़ी सी पीछे आती है और बुलेट आगे जाती है. यहां से सब शुरू होता है. Let's say the force applied by the gun was F1 and the force applied on the bullet was F2. शूट करने के बाद गन पीछे आई F1 फोर्स से और बुलेट आगे गई F2 फोर्स से. The third law tells us that these forces are equal. But imagine अगर दोनों फोर्स सेम है, 100 न्यूटन in this direction, 100 न्यूटन फोर्स इन दिस डायरेक्शन. अगर दोनों फोर्स सेम है तो why does the bullet travel so fast and why doesn't the gun travel in opposite direction so fast? गन भी सेम उससे पीछे जानी चाहिए. बुलेट की वेलोसिटी बहुत ज़्यादा कैसे और गन पीछे जाने की वेलोसिटी बहुत कम कैसे? Because mass of the bullet is come but mass of the gun is large. मतलब मैं और डिटेल में समझाता हूं, ध्यान से देखना. When you shoot, according to Newton's third law, the forces created are same. Yes, जब तुम शूट करते हो the force created on the bullet Fb and force created on the gun Fg are same, but माइनस लगाने से डायरेक्शन बदल जाता है. तो गन पीछे के डायरेक्शन में, बुलेट आगे के डायरेक्शन में. बट फोर्स ऑन बुलेट इज मेड अप ऑफ मास इनटू एक्सेलरेशन and force on the gun is made up of its mass into acceleration. and acceleration की वजह से मिलती है velocity, acceleration की वजह से मिलती है velocity. अब बुलेट का मास छोटा है इसलिए उसको ज़्यादा वेलोसिटी मिलती है, बट गन का मास बड़ा है इसलिए उसको कम वेलोसिटी मिलती है. बट ओवरऑल if you see what remains same, the forces are same and the momentum is same. 2 into 10 is equal to 5 into 4. यहाँ पे मास कम है लेकिन वेलोसिटी ज़्यादा है, यहाँ पे मास ज़्यादा है लेकिन वेलोसिटी कम है, बट ओवरऑल 2 10s are 20 and 5 4s are 20 होता है, therefore momentum is same. तो दुनिया में हर चीज़ में इक्वल फोर्स होता है, ऑपोजिट फोर्स होता है, बट द स्पीड अटेन्ड इज नॉट द सेम. स्पीड अटेन्ड बाय द गन is less, speed attained by the bullet is more, and the reason is law of conservation of momentum. तो यहाँ पे जब आदमी छोटी सी बोट से जंप मार रहा है, the force applied by him and the force applied on the boat is same, और दोनों का वजन भी ऑलमोस्ट सेम है, therefore दोनों पे velocity ऑलमोस्ट सेम होगी, therefore both of them move. But when he jumps from a huge steamer, the forces applied are same, okay, but आदमी का मास कम है तो उसको वेलोसिटी ज़्यादा मिलती है, तो वो सीधा पानी में डुबकी मारता है. लेकिन स्टीमर का मास ज़्यादा है इसलिए उसको बहुत कम वेलोसिटी मिलती है, इतनी कम वेलोसिटी कि वो पता भी नहीं चलता कि वो हिली. इट इज़ एज गुड एज नॉट मूविंग. दैट्स कॉल्ड लॉ ऑफ कंजर्वेशन ऑफ मोमेंटम. So I hope you understood the third law of motion and its discussion of different cases, which is bullet and the gun, the two spring balances, the boat, और ये एक बेकार सा एग्जाम्पल है, एक्टिविटी है कि एक लड़का और एक लड़की दोनों खेल रहे हैं by passing a heavy load full of sand, a bag full of sand. और ये passing the parcel they are playing standing on two crates, two movable trolleys. What will happen when they start playing? When they start playing, he applies some force on the bag. Therefore the bag has some force in it which the girl takes. That girl creates an equal and opposite amount of force. Then she throws, he receives it and कैच करते रहते हैं. अब ये कैच की वजह से because there is less friction in the wheels, यहाँ पे फ्रिक्शन बहुत कम है. 8th स्टैंडर्ड में था रोलिंग फ्रिक्शन. इफ़ यू हैड NCERT टेक्स्ट बुक, the friction is so less that slowly and steadily they get pushing away from each other because the momentum of this bag pushes the entire object behind. This is also according to law of conservation of momentum. So let us now go to the last topic, law of conservation of momentum.
Newton's third law of motion. Aim: to verify Newton's third law of motion using two spring balances. Materials required: spring balance of 5N, spring balance of 10N, and an ion stand. Take the spring balance of 5N. Attach one end of the spring balance to the ion stand. Take the other spring balance of 10N. Attach it to the hook of the first spring balance. Hold it exactly horizontal to the table for viewing the reading of both the balances. Apply a force on the second spring balance. Note the reading of both the spring balances. Force exerted by second spring balance on the first, that is F21, is the action force. At the same time, the force exerted by the first spring balance on the second, that is minus F12, is the reaction force. Tabulate the observations. Gently increase the force to 3N and note it down in the observation column. Repeat the experiment for 4N and 5N. Tabulate the observations. It is observed that both action force F21 and reaction force minus F12 are equal and opposite. So F21 is equal to minus F12. Hence, Newton's third law is verified.
Only question you need to ask yourself while studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table and the subject exerts an upward force on the object. There are two forces that result from this interaction: a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is the only object here and there's no second object. But that's not correct. The wings of the bird push the air downwards and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right, it exerts a forward force on the bullet. And the bullet exerts an equal and opposite reaction force on the gun. And this exists in recoil of the gun. A perfect example of Newton's third law. But hold on. If the force exerted by the gun on the bullet is the same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration. Or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor? Not really. And I think you know why.
Today we're going to demonstrate Newton's third law of motion, which says every action has an equal and opposite reaction. It's the principle that sends rockets to the moon. If you want to try this at home, this is what you need. When I release my fingers, air pushes out of the balloon. That's our action. Our reaction is that the balloon moves with the same force in the opposite direction. If you want to learn more about Newton's third law of motion or ask me a question, check out scientistsusan.com.
Now what does law of conservation of momentum say? There are two balls which are already traveling in the same direction. Ball A, ball B are traveling in this direction, एक के पीछे एक. A का initial velocity is UA, B का initial velocity is UB. A का mass is MA, B का mass is MB. Do you think this ball has any momentum? क्या A के पास momentum है? Momentum means mass into velocity. A के पास mass भी है और velocity भी. So momentum initial of A is mass into velocity. क्या B के पास momentum है. Initial momentum of B is mass into velocity of B. भूल जाओ कि मोमेंटम है, सिर्फ इतना याद रखो कि दो बॉल एक दूसरे के पीछे अलग अलग स्पीड से जा रहे हैं और एक ही स्पीड ज़्यादा होगी तो वो बी से टकराएगा. दे बैंग विथ ईच अदर, भटकाया. एंड व्हेन दे बैंग विथ ईच अदर, द थर्ड लॉ कम्स इनटू मोशन. द मोशन नहीं, एक्शन. द थर्ड लॉ कम्स इनटू पिक्चर. थर्ड लॉ क्या कहता है? एक्शन is equal to reaction but opposite direction. Action and reaction are equal and opposite. मतलब equal in magnitude but opposite in direction. तो A ने B पे कितना फोर्स डाला? FAB. A ने B पे कितना फोर्स डाला? FAB. और B ने A पे कितना फोर्स डाला? FBA. और ये दोनों थर्ड लॉ के हिसाब से इक्वल है. ठीक है. और टकराने के बाद दोनों की स्पीड चेंज हो गई और वापस उसी डायरेक्शन में नई स्पीड से चलने लगी. और नई स्पीड है VA, VB. द मास रिमेन्स सेम MA, MB. Do you think their momentums have changed? Yes. Momentum is mass into velocity और velocity change हो चुकी है. तो final momentum of A has become mass into final velocity. And final momentum PF of ball B has become mass into final velocity. Okay, फिलहाल momentum को भूल जाओ. तो मैं पूरा सिनेरियो वापस लिख के बता रहा हूँ, ध्यान से देखना. वंस अपॉन अ टाइम देयर वर टू बॉल्स गोइंग इन सेम डायरेक्शन. मास ऑफ बॉल वन इज MA, सेकेंड इज MB. इनिशियल वेलोसिटी UA, इनिशियल वेलोसिटी UB. फिर वो दोनों टकराते हैं और टकराने के बाद they continue their journey but different velocities. तो final velocity VB, VA. मास अभी भी वही है MA, MB. जब टकराए तो थर्ड लॉ ऑफ मोशन केम इनटू पिक्चर. ये तुम्हें बाय हार्ट करना है लिख के. एज पर थर्ड लॉ FAB इज इक्वल टू माइनस FBA. मतलब A ने B पे जितना फोर्स एक्ट किया वो सेम फोर्स B ने A पे किया बट इन ऑपोजिट डायरेक्शन, इसलिए माइनस लगाना पड़ता है. बट व्हाट इज फोर्स? इट इज मास इनटू एक्सेलरेशन. हु सेड दिस? मास इनटू एक्सेलरेशन. दिस इज बिकॉज ऑफ सेकेंड लॉ ऑफ मोशन. सेकेंड लॉ में F इज इक्वल टू MA का डेरिवेशन है. but acceleration is v minus u by t. वो तो मोशन चैप्टर में देखा था. एक्सेलरेशन इज v माइनस u बाय t. बाय टी कट हो जाता है बिकॉज टाइम टेकन इन दिस बैंगिंग इज सेम. तो क्या बचता है? एम ए इंटू वी ए माइनस एम ए इंटू यू ए is minus mb into vb plus mb into ub. माइनस और ये माइनस की जगह बदलो तो एम ए वी ए प्लस एम बी वी बी इज इक्वल टू एम ए यू ए प्लस एम बी यू बी. मतलब फाइनल मोमेंटम ऑफ ए प्लस फाइनल मोमेंटम ऑफ बी, जो हमने पहले ही देखा था, लिखा था मैंने, इज इक्वल टू इनिशियल मोमेंटम ऑफ ए प्लस इनिशियल मोमेंटम ऑफ बी. मतलब टोटल फाइनल मोमेंटम इज इक्वल टू टोटल initial momentum, and this is called the law of conservation of momentum. Total final momentum and total initial momentum of any two objects is same. तो कोई भी टकराने के पहले और टकराने के बाद मोमेंटम सेम रहता है. So this derivation is not given in textbook properly, so look at the video and copy 2-3 times to remember it by heart. That's the end of the chapter. I'm attaching few extra videos because they're interesting and tells you a little more about the concepts of momentum, third law, and law of conservation of momentum. In next lecture, we will do the numericals in details. See you.
Law of conservation of momentum. Objective: to learn the law of conservation of momentum. Momentum is defined as the motion of the mass of an object. Because all objects have mass, any moving object will also have momentum. The law of conservation of momentum states that the total momentum of two or more objects acting upon one another will not change, provided there are no external forces acting on them. In other words, when two objects collide, their total momentum before the collision will be the same as the total momentum after the collision. Let's consider two cars of different masses, a bigger one, m1, and a smaller one, m2. Imagine the cars are moving in the same direction, but with different velocities, u1 and u2 respectively. Because momentum is the product of mass and velocity, the momentum of the bigger car can be expressed as m1 into u1, and the momentum of the smaller car can be expressed as m2 into u2. To determine the total momentum of both cars would be m1 u1 plus m2 u2. Now let's imagine that our two cars are colliding. During the collision, the bigger car will exert a force F1 on the smaller car, and the smaller car will exert a force F2 on the bigger car. As a result of the collisions, the velocities of the cars will change. So, we'll represent those as V1 and V2. Force is the product of mass and acceleration. In our example of the collision, the force of the bigger car will be expressed as F1 is equal to m1 into v1 minus u1 by t, with t representing time. The force of the smaller car during the collision will be expressed as F2 is equal to m2 into v2 minus u2 by t. According to the Newton's third law, Each action will have an action that is equal and opposite, meaning the forces can be expressed as F1 is equal to minus F2. Because both forces are equal and opposite, we can also write them as M1 into V1 minus U1 by T is equal to minus M2 into V2 minus U2 by T. We can cancel T, the common factor of time in the equation. M1 into V1 minus U1 is equal to minus M2 into V2 minus U2. The equation can then be simplified. M1 V1 minus M1 U1 is equal to minus M2 V2 plus M2 U2. And it can be written as M1 into V1 plus M2 into V2 is equal to M2 into U2 plus M1 into U1. From this equation, we can see the total momentum for both cars before and after the collision did not change but was conserved, thereby proving the law of conservation of momentum. Summary. The law of conservation of momentum states that the total momentum of two or more objects acting upon each other does not change, provided no external forces act upon them.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm gonna try the golf ball on top of the bouncy ball on top of the basketball. And then I'm gonna explain how it's related to a supernova. Did you see that? Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!